So let's continue with the proof of this, which is a biconditional. Let us start by assuming first that x is a limit point to A. Well, we will then construct some convergent sequence in cap A whose limit is x. Well, the way to do that is rather easily understandable. Well, this is a limit point of A. No matter what neighborhood of x I take, it contains points of cap A. But since we're in a metric space, well, we know that we can replace neighborhoods by epsilon balls. We have a proposition saying that. So I can take a sequence of epsilons, which actually gets arbitrarily small. Say, I can refer to epsilon n by 1 over n. And for each n, I can find a point in cap A, which is closer than epsilon n, that is 1 over n to A. And then that sequence, well, that will actually be convergent to x, and it will be a sequence in cap A. So for each n, set epsilon n. Well, I can take this 1 over n, 1 over 2 to the power n. Well, it should be something as n tends to infinity. This should converge to 0, that's all. This will be positive. For each n in n, since x is a limit point of A, there is some xn which is in the epsilon n ball about x intersected with A. Since I have chosen for each n the term x sub n in cap A, x sub n is the sequence in A. Now, what remains to be shown is to complete the proof of this direction that x sub n converges to x. Okay, now let epsilon greater than 0 be given. Now we use the Archimedean property of real numbers, which we decided to take as granted given to us. Given any positive number, there is a large enough natural number such that 1 over that natural number is less than epsilon. Now, there is some k in n with 1 over k less than epsilon. I can take this cap k as the cap k in the definition, then for any n in n with n larger than or equal to k, what do we have? M of x sub n. Well, x sub n was chosen in the epsilon n ball of x. Well, by the choice of xn, this will be less than epsilon n. But epsilon n is 1 over n. But if n is larger than or equal to cap k, this will be less than or equal to 1 over cap k. But we have chosen cap k such that 1 over cap k is less than epsilon. So, well, this simply says x sub n is in the epsilon ball about x for each such n. That is, by definition, x sub n converges to x. Okay, so we have shown if x is a limit point of cap A, then there is some convergence sequence xn intersect with limit x. Now let's also consider the converse. Conversely, assume that xn is a sequence in A and xn converges to A where A is something in X. Now we need to show the limit of any convergence sequence, thus this A, is a limit point of cap A. Okay? But this being the limit point of cap A, that's equivalent to showing that for any epsilon ball about A, that should have a non-empty intersection with the set cap A. So take any epsilon positive. What we wish to show is that the epsilon ball about A intersected with cap A is non-empty with respect to n. What we know is that xn converges to A. Now, since xn converges to A, there is some natural number k such that for all natural numbers larger than or equal to k, we have xn in the epsilon ball about A. But I can take just any one of them, except cap k, for example. Well, by this, it will be in this epsilon ball. But by construction, by definition of the sequence, it's a member of cap A as well. So, x sub k, say, any one of them, this is in the epsilon ball about A intersection A. That is, the epsilon ball about A with respect to M intersection A is non-empty. Thus, A is a limit point of cap A, completing the proof. Let me also note what we mentioned preceding the statement of this proposition: characterization of closed sets in terms of convergent sequences in the set considered. Now let Xn be a metric space and A a subset. Now A is closed if and only if the limit of every convergent sequence in A belongs to A. But this is just the conjunction of the preceding proposition with the characterization we had last time that a set is closed if and only if it contains all its limit points. Because the limits of convergent sequences in A, the totality of them, that's equal to the set of all limit points, and this result follows. Proof: conjoin the above proposition with the proposition concerning the equivalence between closedness of a set A and A containing all its limit points. Now here, if the focus is on points which are arbitrarily close to a set, well, if a point belongs to the set, then it's arbitrarily close. That's what follows from our definition of a limit point, because if it belongs to a set, well, it's either an isolated point or a cluster point of the set. It's a limit point. Now, what's more crucial is points outside the set, whether they are arbitrarily close to the set or not. But if a point which does not belong to the set is a limit point, it has to be cluster points. So cluster points are actually more crucial than, well, because isolated points, they belong to the set. Well, a limit point, well, which is a cluster point and which is outside the set? That seems to be, and here, it says, well, you cannot have. If the set is closed, then all the cluster points must belong to the set. They cannot be outside. But, well, if a set has no cluster points at all, can you say anything about it in terms of topological terms? It must be closed. It contains all the isolated points. Well, there are no cluster points. The empty set is contained in the set, so it must be closed. So, well, do we know any such metric space where this happens? Well, with the discrete metric it happens. We have seen, well, actually, the name discrete came from that fact. Take the discrete metric space or the discrete topological space, they're the same. Take any set. We have seen every point of the set is an isolated point. That's why we refer to that structure as being discrete. And it has no cluster points. Take any x, take singleton x, that's a neighborhood. Take x out, nothing remains. So singleton x minus singleton x intersected cap A, that's empty, has no cluster points. So it will turn out to have some circumstances which actually will guarantee the existence of cluster points of a set, and that will take us to some result which you're familiar with from calculus. But, well, in a metric space, as we have seen, that does not happen all the time. Well, but we'll have some important result which is peculiar to Euclidean spaces. But for that, we first need a definition. The definition of boundedness of a set in a metric space. Now let Xm be metric space. And A a subset. Now we say that A is bounded well, let me write this in full, it's the definition. With respect to M, if there is some real number which is an upper bound of the set consisting of all possible distances between 2 points according to the metric M in this set. Well, such that for all xy in A, mxy is less than or equal to M. So no matter what 2 points you take, the distance according to the metric M should not exceed M. So this is an upper bound to all possible distances according to the metric M between 2 points in this set. Now, something familiar. Maybe it's not the version that I will write now. That may not be familiar, but it's sequence version that will definitely be familiar. Theorem. This says every bounded infinite set in Rm has a cluster point. Now, we had the convention, if we talk of a Euclidean space and do not mention the metric, it's the usual metric, but let me, with respect, let me write it here to the usual metric D. Is this familiar? Okay, now let me put it the other way around. We have not defined what the bounded sequence is, but in calculus, what can you tell about the convergence properties of a bounded sequence? It need not be convergent itself, because take 1 minus 1, 1 minus 1, and so on. That's not convergent, it's bounded. That is the values of the terms, that set is bounded. But what can you tell about that? About a bounded sequence in Euclidean space, it has a convergent subsequence. How is that theorem known by whose names? It's Bolzano-Weierstrass theorem. Well, actually, it stems from this. We'll see that we'll need this to prove that every bounded sequence in Rm has a convergent subsequence. So this is Bolzano-Weierstrass. Now, we will not go into the proof of this, but it's simple. I will just sketch the proof and you can fill in the details. Now, well, we wish to draw a picture. Well, let's have R2. But you can see how that can be generalized to Rm. Now, the first thing is, since this set is bounded, I can find a square in the plane such that all the points of the given set, of the given, say, A is bounded and infinite. Okay, I can confine that to some bounded region, which I can take large enough and as a square. Now, let me forget about these axes. Let me take the midpoint of each coordinate and partition this into 4 subregions. Well, the set is infinite. Some part of that is here, some here, some here, some here. What can we tell? Well, at least in one of these 4 parts, it should have infinitely many members again. Well, it might have in all, but there's at least one. Suppose it's this. Then continue with taking halves of both coordinates. But this set had infinitely many members in this region, so it must have infinitely many members in one of these. Then do that and continue that, and then you will get, well, if I call this B1, the entire thing, then this will be B2, that will be contained. This will be B3, and then say if it's this, it will be B4 and so on. Each of these will contain infinitely many members of the set. You can show easily that the intersection of the BI's is non-empty, and any point in this intersection, that will be a cluster point of the given set. But as I said, formally we will keep this outside the realm of the course, but it's pictorially it's easy. Well, if it's Rm, well, if m is 1, then you just take an interval, take half of it, then one part contains. Well, if it's R3, then you take a cube. Well, if it's Rm, you take a generalized m cube and do the same thing. No matter how large m is, well, each time you do this, you will get finitely many, a collection of finitely many subcubes or subsquares. Well, if the set is infinite, at least one of them should contain infinitely many members. That's it. Is this valid in general in metric spaces? No, take Rm with m, where m is the discrete metric. And in fact, take as A the entire thing. Is A bounded? Yes, if it's the discrete metric, m of xy is less than or equal to 1. It's either 0 or 1. Now for all xy in A, mxy is less than or equal to 1. So A is bounded and infinite. Well, but as we have just seen, it has no cluster points at all. Has no cluster points. Now, in order to get the subsequence version of this result, what it imposes on subsequences of a bounded sequence in Euclidean space, now we first need to, again, define what a subsequence is. Any questions so far? Now, if this is a sequence, what do we mean by a subsequence? Well, what we do is we take some of these, say x7, and leave out some. But we keep this x2, x7, whichever we choose, to belong, to take part in the sublist. Well, we keep the order. Well, if 2 is less than 7, then x2 comes, and then comes x7. Okay? So, to formalize that, let me first introduce monotonicity properties of sequences in Euclidean spaces, which we will need anyway. Now, let xn be a sequence in some Euclidean space, Rm. But this xn, that was just a shorthand notation for a function like this. Here we have an order structure. Here we have the extension of that order structure as well. So whenever we have actually a map from R to R, well, when do we refer to that as monotonic? Well, if it's increasing, if it's non-decreasing, the weak form, if it's decreasing, or if it's non-increasing, the weak form of increasing. Now we can introduce that in here. We say that xn is increasing if this map is increasing. That is, if for all mn in n, m, well, let me write nn prime, because here we have rm. n prime, when n is less than n prime, this should imply x sub n, which is x sub n, is less than x sub n prime. This now is the relation extended to vectors, because m might be larger than 1. So we say that it's decreasing now everything is the same, but this time the implication should be that xn is larger than n prime. We say that it is non-decreasing now here, if this time actually we allow equality between xn and xn prime. That's the weak form of this, of increasing. And finally, we say that it's non-increasing if this time this is reversed. This is just preservation of the order structure of n under x in one of these 4 cases. Now, we can define what the subsequence is in precisely mathematical terms without any informal description. Now, let A be a non-empty set and now let me go back to this functional notation, x on n with values in A, a sequence in A. Now what do we do here? What we do actually is we take a sequence in the set of natural numbers, which is here 2, 7, and whatever we take. Okay? But that sequence should be increasing. Okay. Now let R, what will be sequence in the set of natural numbers itself be? Well, it will be, well, this domain, that should be natural numbers by definition of a sequence, but its in natural numbers again. Let R on n in n be an increasing sequence in n. We refer to what as a subsequence of this? Well, we first consider this increasing sequence and then apply x. That is, we take the composition of x with R to the sequence, which is the composition of them. Well, R applies to n with values in n. Here, 1 is sent to 2 under R. Then you'll look to the image of 2 under the sequence, x2. Here, 2, if this is the second term we take in the subsequence, 2 is sent to 7, R of 2 is 7. Then you apply x, you get x7. That is this composition, which will be a map on n to a as a subsequence of x. Now, if we utilize the convention we had in passing to the usual notation of sequences, here what do we have? Now, for any n in n, now let's look at this. X composition Rn. How is the composition of functions defined? That is x of R of n. According to our convention, how do we denote Rn? As R sub n. How do we denote x of R sub n? X of R sub n, we denote that as x sub R sub n. So, we will denote this as x sub R sub n, a subsequence of the given sequence. Okay, so this is the usual notation in calculus and elsewhere we use for subsequences, but it's consistent with this functional notation. Now, in order to have the implication of this theorem in the world of sequences, we need the notion of a bounded sequence, because we have the notion of a bounded set, but we need to define bounded sequences as well. But that's easy to do. We will consider the set consisting of all the terms of the sequence. If that set is bounded, we will refer to the sequence as a bounded sequence. Now let Xn be metric space and Xn a sequence in cap X. We say that Xn is bounded with respect to m if the set of x sub n's n in n is bounded with respect to m, because we have defined what this means. Okay? Now we'll have two simple but useful propositions. The first one is, if you start with the convergent sequence with limit, say, a, any subsequence will be convergent and will have the same limit. Let Xm, again, be a metric space. Xn, a sequence in X. A member of X, and X bar sub n, a subsequence of X sub n. Now, if X sub n converges to A, then X bar sub n converges to A as well. Well, that's what we know for sequences in real numbers and in Euclidean spaces from calculus. Although the proof is simple, let's go through that to see actually how this definition of a subsequence comes into play. Assume that Xn converges to A. The claim is that X bar n converges to A as well. Okay? Let epsilon greater than 0 be given. Our aim is to find some cap k, a natural number, such that whenever n is a natural number larger than or equal to that cap k, X bar sub n, its distance according to m from A will be less than epsilon. But what we know is, well, that Xn converges to A. Okay, now there is some k in n such that for all n larger than or equal to k, m of xna is less than epsilon. Will this same cap k work for X bar sub n? Let's see. Okay, so this is what we know. Now, take any n larger than or equal to k. What do we know about the sequence R sub n? It's increasing. So, as R sub n is increasing, is an increasing sequence, what do we have? How does R sub n compare with R sub k? R sub n is larger than or equal to R sub k. But how is R sub k and k related? Well, that's larger than or equal to k. It's an increasing sequence, so the R sub k, well, in the tightest case, it's k. It's okay, implying that M of x sub r sub n, A is less than epsilon. So x sub r sub n, that converges to A. So that's true in any metric space. If a sequence is convergent with respect to the metric, then any subsequence is convergent and has the same limit. That. Now, let me just write the statement of the theorem, which is also known as Bolzano-Weierstrass theorem. Now, let Xn be a bounded sequence in Rm. Now, Xn has a convergent subsequence. As no metric is explicitly mentioned, according to our convention, we mean the usual distance. Well, we will go through the proof of this quickly, but not now. But this being bounded, this sequence, that means if you form the set consisting of the terms of the sequence, that's a bounded set. But Bolzano-Weierstrass theorem in this form may not apply to that set because this says bounded infinite. But if the set consisting of the terms of the sequence is finite, then there is at least one member of that set which occurs infinitely many times. So we can just take those terms which take that value, well, that will be subsequence, and a constant sequence will be convergent. Otherwise, it will be an infinite set, and according to here, it will have a cluster point. Well, in that case, we can construct a subsequence of x sub n, which actually converges to that limit, to the limit which is just a cluster point whose existence we know. But we'll continue with that in 2 weeks.